Chapter 9, The Atom. The photoelectric effect. The photoelectric effect is the emission of electrons from a metal surface when light, in this case ultraviolet light, shines on it, the surface. An illustration of the photoelectric effect. The yellow light is meant to be shining on a surface, and the blue particles represents electrons that are ejected from that surface. Additional information. The photoelectric effect, color and intensity. Electrons are emitted no matter how faint the light source, firstly. The speed of the resulting electrons is a function of the wavelength of light. Long wavelengths yield slow-moving electrons. Short wavelengths yields fast-moving electrons. Another illustration of light frequencies. First, in the top figure, we have dim blue light. And what we find with dim blue light, the electrons that are ejected are moving fast-moving electrons. Here we have bright red light, and what we find that more electrons are emitted, but they are moving slowly. Okay, the photoelectric effect continues. The discovery of the photoelectric effect could not be explained by the electromagnetic theory of light that existed at that time, as worked out by James Clerk Maxwell. The quantum theory of light, then. Albert Einstein developed the quantum theory of light in 1905 based on the hypothesis from Max Planck. And Max Planck's figures very strongly. And in fact, pretty soon, you will see what we call the Planck's constant. Now, light quanta comes into being. Light emitted by a hot object is given off in discrete units called quanta. And next, the higher the frequency of the light, the greater the energy per quanta. All the quantities associated with a particular frequency of light have the same energy. So this gives the notion then that light carries energy. Now, the fundamental equation is that E equals H times F. And E here is the energy that's involved. And H is this Planck constant that I spoke of earlier. And it has been measured. Planck constant is a very small number. 6.63 10 to the negative 31 joules times a second. And F here is the frequency in cycles per second, or the equivalent unit in hertz. Now the word photons. Einstein explained Planck's hypothesis by proposing that light could travel through space as quanta of energy called photons. These photons, if of sufficient energy, could dislodge electrons from a metal surface, causing the photoelectric effect. That's what we mean. So as opposed to a wave striking the surface and dislodging electrons, it is now believed that these photons strikes the electrons in the surface of the metal, dislodge the electron from the surface of the metal, and that is referred to as the photoelectric effect. And the basic equation we have now, Einstein equation for the photoelectric effect, is H times F is equal to the kinetic energy of the ejected photon plus the work function, W, is the energy needed to dislodge the electron from the metal. Because if an electron tries to leave the surface of the metal, the protons in the metal try to pull them back in. So it takes energy to dislodge the electrons. Although photons have no mass and travel with the speed of light, they have most of the other properties of particles. The average frequency emitted by a 100-watt light bulb is 5.5 10 to the 14 hertz. How many photons per second does this light bulb emit? And you're going to find it's a huge number. So we work through the mathematics. We calculate the energy first, and the energy comes out to be 3.6 10 to the negative 19 joules. And then we can calculate then that there's 2.8 10 to the 20 photons per second are emitted by this 100-watt light bulb. That's a large number of photons. What is light? Light exhibits either wave characteristics or particle photon characteristics, but never both at the same time. The wave theory of light and the quantum theory of light are both needed to explain the nature of light and therefore complement each other, but they're never used in the same experiment. They're always one way or the other. And so we live with now this duality nature of light. Example here of wave and quantum theory of light. The top figure represents the wave pattern, if you will, of a candle of light striking a surface, and the second one, photons leaving the candle, striking the surface and dislodging electrons. Now here's come the other aspect, the Broglie waves. Now these are going to be matter waves. In 1924, the French physicist Louis de Broglie proposed that moving objects behave like waves. And now we have what's called the de Broglie wavelength of a particle of mass m with speed. The mere fact that the particle is moving and has mass, it now has what we call the de Broglie wavelength, which is equal to h divided by m times v. Matter waves are significant only on the atomic scale. So on the microscopic scale, the scale we live on, matter waves are insignificant. And we'll go through a calculation to see that in a moment. Example, find the de Broglie wavelength of a 45-gram golf ball. And then B, find the de Broglie wavelength of an electron moving at 10 to the 7 meters per second. For that of the golf ball, it is 4.8 10 to the minus 34 meters. Far too small to be registered or used in any experiment. But for that of an electron, the calculation yields that lambda is 7.3 10 to the negative 11 meters. That is just about the same size of an atom. Therefore, the de Broglie wavelength will interfere with an atom. Wave function. The quantity that varies in a matter wave is called the wave function psi in quantum mechanics. And the square of the wave function is called the probability density. For a given object, the greater the probability density at a certain time and place, the greater the likelihood of finding the object at that time and place. This is an example then of a matter wave. Top figure is just a particle mass m moving with speed v, and the bottom represents the psi, and the wave then is extended in space. The wavelength is shown, and the largest value indicate where the particle is most likely to be located. Spectroscopy is an instrument that disperses light emitted by an excited gas into different frequencies that light contains. Here's an illustration. You have a gas light bulb here. The light comes through a small opening in here we call a slit. The white light, then you can't tell. All the colors are there, but white light masks the feature that the colors are there. The light impinge on a prism and are dispersed here, that you can see the actual colors. The emission spectrum consists of various frequencies of light given off by an excited substance. an illustration of an emission spectrum. Electron orbits are identified by quantum number n, and each orbit corresponds to a specific energy level of the atom. Electrons cannot possess energies between specific energy levels, or what we call orbits. An electron can be raised to a higher energy level by absorbing a photon or by emitting a photon and fall to a lower energy level. When an electron jumps from one orbit to another, the difference in energy between the two orbits is h times f, where f is the frequency of the emitted or the absorbed light. An illustration then of the orbits then around a nucleus. The nucleus is in the center. Then you have the ground state orbit, the first higher level orbit, on and on and on. An illustration then.
An atom emits light when one of its electrons drops from an upper to a lower orbit. The light is energy that was previously stored in the electron's orbital motion, but which is released as the orbit shrinks.
The ground state, an atom having the lowest possible energy, is in its ground state. An atom that has absorbed energy is in an excited state. Here, a rendition. This atom is thought to be in this state here, and it's in n equals 1 state. This is thought to be in an upper level, the n equals 2 state. The electron is farther from the nucleus in a satisfied orbit, and it's in an upper level state. Here, we thought that the electron has been moved from this ground state to the upper level state. And in this rendition, the electron has come back down to the lower level state with the emission of a photon. Another illustration.
An electron, which is in a higher energy level than its ground state, is said to be in an excited state. When an electron moves from a higher state to a lower state, a photon is emitted whose energy is equal to the energy difference between the initial and final states. This principle is illustrated here for an atom through the mechanical analogy of a ball on a staircase. The transitions which produce photons of visible light for the hydrogen atom are referred to as the Balmer series.
Now I want to show you the origin of the emission and absorption spectra. The first is the idea that an atom is already in an upper level state, and what happens? The atom quickly drops to a lower level state with the emission of a photon, and now we have what is called the emission spectra. Here, you have a photon comes in, strikes an atom, raises it to an upper level state, and now you have that energy missing. And so this represents an absorption spectrum. Finally, the electron waves an orbit. An electron can circle a nucleus only in orbits that contains a whole number of the Broglie wavelengths. The quantum number n of an orbit is the number of electron waves that fits into a given orbit. So what we've tried to do is build up the notion of an atom by having a nucleus, and the electrons can't be anywhere they wish to be outside the nucleus. They have to be in specific orbits, and these orbits are represented by specific energy levels. That brings me to the end of this presentation.